SwayamPrabha. Digital India. Educated India.
Hello everyone. So, we are discussing the water filtration using nanofibrous membrane, which has been developed in house. So, that experimental work, experimental development which we are discussing, and this we have reached up to part 3, where we are discussing the development of electrospun nanofibrous membrane on non-oven substrate. This part we have discussed. Before this, what we have done in this study. So, first part, that is stage 1. Stage 1 we have discussed the non-oven fabric, needle punch fabric, how non-oven fabric actually removes the solid and turbidity in water, and we have optimized the parameters like depth of needle penetration, needle density. So, this we have done in the part 1, and also in part 2 what we have discussed, that antibacterial non-oven, that is silver nanoparticle embedded polyester fiber. From that we have developed non-oven, and also by reducing the fiber, that is surface etching, we have that by exposing the nanoparticle, how the antibacterial effect has improved. That part we have discussed in part 2, and now we are discussing the development of electrospun nanofibers membrane on non-oven substrate. This part we are now discussing, and in the last part what we will discuss, the design and development of a prototype 2-stage purification system. That is, stage 1 is that turbidity and solid removal by wicking, that part is there, and stage 2, this is stage 2, stage 2 which consists of all the 3 parts. So, where that non-oven nanofibrous membrane was developed. So, the electrospinning that we have discussed. So, what are the advantages of the electrospinning? In the last section we have discussed this electrospinning advantage, that is high porosity, high surface area to volume ratio, small pore size we can develop, that is we can restrict the smaller particle. So, we can have very fine low weight and good mechanical properties, because if we use the substrate, so that we can retain this structure, and that the precise control we can do by controlling the diameter, morphology, composition and porosity of the membrane. So, this we have discussed already. Now, here the problem statement is that direct spinning, electrospinning of chitosan is difficult due to that internal H bonding between OH and NH2 group. So, that actually results poor spinability. So, 100% chitosan, it is not possible for electrospinning. We have used PLA, we have blended with the PLA. So, the main challenge was that improving the spinability of chitosan, and then that we have to identify the copolymer and solvent for chitosan. So, that was the main challenge. So, we have optimized that. Now, if we see the most adaptable environmental friendly polymer is PLA, that is it is most adaptable and it is environmentally friendly. So, we have used PLA along with the chitosan. Okay. So, the reason for using PLA is that it is environmentally safe, then we can have in a large quantity. The resources are very common resources, sugar beet, sugar cane, okay, and these are degradable. So, biocompatible, so renewable. So, that does not actually release any toxic component. Most recognized green material in current era. So, PLA we have selected to blend with the chitosan. Now, these are different blend percentage we have used. 100% PLA sample A, sample B 50% PLA, 50% chitosan, and sample 3 30% PLA, 70% chitosan, and sample D 20% PLA and 80% chitosan. So, first what we have done, we have tried to optimize the blend proportion. We have used the electrospinning process. So, here the polymeric solution we have used with all different proportions, and in the electrospinning that high voltage of 25 kilovolt we have used and kept the spinneret to collector distance 10 centimeter, and flow rate we have kept 100 microliter per hour, temperature 29 degree Celsius, almost room temperature, and humidity 45%. So, there is no special control on humidity and temperature required here in this system. So, this is the electrospinning setup and high voltage power supply is there, and the process we have already discussed. And after this this system, when voltage is applied, so nano wave is collected on the collector surface and we can get the nano wave. Now, what we have done, the surface morphology study. If we see the 100% PLA, so 100% PLA spinability is, there is no problem. The problem was with 100% chitosan. So, for reference what we have done, we have used 100% PLA, keeping all the process parameters same as I have discussed. These are the process parameters, voltage, okay, distance, collector distance, and flow rate, everything we have kept constant. And what we found, the diameter, mean diameter of this fiber, the nanofiber which we get, it is 310 nanometer. Okay. This is the nanofiber diameter. Then what we have done, next sample with 50% PLA and 50% chitosan, with 50% PLA and 50% chitosan, the average diameter which we have got 220 nanometer. Okay. This is the 220 nanometer, still it is a larger size. And next sample which we have got 70-30, and in 70-30 we could get very fine fiber diameter 131 nanometer. So, 70% chitosan and 30% PLA, and we could not spin the 80-20 chitosan and PLA, because what we found, the if the chitosan proportion is increased to 80%, the spinability is dropped. Okay. So, that is why the 70-30 we have reached up to the 70-30, and what we found, with the increase in chitosan percent up to 70%, the fiber diameter consistently reduces. So, that is why we have used 70-30 for our as an optimum value, 70-30 chitosan PLA blend. Now, if we see the this fiber, so 131 nanometer, smaller nanometer. So, here we can see the average diameter of chitosan PLA nanofiber decreases with increasing chitosan content, but maximum up to 70%. If we go beyond 70% and 80%, we have observed that spinability was dropped. So, the reason being here, the chitosan has amino group in its molecular chain, and what happened, hence its solution is an acidic solution, carries positive charges. So, here it carries the positive charges because of the amino group. So, in acidic solution it is carrying positive charge, and what will happen there, this will increase the charge density of the polymer jet. So, at the jet it will increase the charge density and reflects in increasing the conductivity. So, in the jet when high voltage is applied, so due to this positive charge, increased charge density, the conductivity will increase, and then what will happen, that is why the 70-30 chitosan PLA blend ratio give more fine and uniform morphology due to the conductivity here, higher conductivity, the stretching becomes more, and that results lower fiber diameter. Now, try to see the mixture where the chitosan and PLA has mixed properly or not, that we have done through different analysis. So, FTIR analysis shows here, you can see here this shows the red color curve, it is shows a PLA's FTIR. So, here the backbone, it is this is backbone ester group, these peaks are there, this is the backbone ester group of PLA, the red color. Okay. Now, here and this is the for chitosan amide 1 and amide 2, the peaks are given here 1680 and 1540. Now, when we see the combination, that is a blend, chitosan PLA blend. So, where in this spectra the chitosan PLA nanofibrous membrane, when we used for FTIR analysis, the peak at 1759, here is the peak and this was the peak in the blend, which is the peak for the PLA. So, that belongs to carbonyl group in PLA. So, that shows the presence of PLA there, and peak at 1680, it represents the amide 1 group, which is in chitosan. Okay. This shows this the presence of both the peaks here, and that results that this is the perfect blending of chitosan and PLA, and this is tested, this is a nano wave is tested. So, proper blending took place. So, from this FTIR, so we have confirmed that the produced that wave, nano wave as a chitosan and PLA nanofibrous wave are homogeneous blend of chitosan and PLA. Whatever the proportion we have given, it is a homogeneous blend. So, first what we have done, we have optimized the proportion where the spinability is good and fiber we can produce was finer fiber with a 70-30 chitosan and PLA. So, chitosan PLA blend 70-30, that was based on the fiber diameter and spinability, and then we tried to prove that the blend whatever we have got the wave, it is the perfect mixture, homogeneous blend of chitosan and PLA. Now, we can see here this is this actually EDX, this analysis shows that presence of carbon, oxygen and nitrogen. So, this in the chitosan and PLA, whatever the blend, as per the blend proportion, the weight percent we could get, and which is actually as per the homogeneous blending. This shows the perfect blending was there in the nanofibrous wave. That is carbon, oxygen and nitrogen peaks were observed, which were in line with the blended material of chitosan and PLA. So, as per the blend, that carbon and oxygen and nitrogen peaks were observed. So, which confirms the homogeneity of chitosan PLA nanofibrous membrane. So, we have reconfirmed this from EDX and FTIR. So, both the analysis actually confirmed that the blend proportion were. So, both the analysis confirmed that the blend proportion was homogeneous and the nanofibers which we have developed were perfect homogeneous nanofibrous membrane. Next stage, so we have developed, we have optimized 70-30 chitosan PLA and we have developed perfect nanofiber. Now, next stage was that we wanted to incorporate silver nanowire inside the nanofiber. So, nanofibers we have developed. We now at this stage our main idea was to incorporate the silver nanorod within the nanofiber, carbon PLA nanofiber. So, chitosan PLA. So, chitosan is antimicrobial, it is well known, and silver if we can incorporate, as we have earlier seen that silver particle acts as antimicrobial agent. So, if we can incorporate, then it will have very good antimicrobial activities, that was our assumption. So, our next objective was to develop nanowire, silver nanowire. Now, here what we have done, we have used glycerol as a solvent and polyvinyl pyrrolidone. So, that is PVP, which is used as reducing agent. So, this is the method, and here it is used a solvothermal method. So, solvent used at higher temperature. So, both solvents reactivity will be there, glycerol is a solvent, and also we have the experiment was carried out at 90 degree Celsius, that mixture. Then we have reduced the temperature to 50 degree Celsius, where we mixed the silver nitrate. Silver nitrate was mixed by drop wise. It is we are here it is silver nitrate was mixed, and then we have added the mixture of glycerol, sodium chloride and water, very small quantity of water. So, that by drop wise we have mixed. First 10 ml of glycerol we have added, 59 milligram of NaCl and 0.5 ml of water drop, small water drop, and again it is heated at 210 degree Celsius for 25 minutes. That was the temperature we have kept here, and then we have left this, cool down this solution and left it for 1 month. So, this gray solution was after heating for 25 minutes, the greenish gray solution was produced. This gray green solution kept undisturbed for 1 month. So, after 1 month what we have observed? We have observed the formation of nanorod, very fine nanorod were observed. So, we can see this type of nanorods, that is silver nanorods, pure silver nanorods were formed. Now, we can see that scanning electron microscope, it says that nanorod is there, and TEM image it's you can see that this is the nanorod. Now, here the length of the fiber range from 7 to 12 micron and diameter is typically around 51 nanometer, 51 plus minus 7 nanometer, within that range, and with the very good aspect ratio of 159. In average aspect ratio we have got 159, and this result shows that we could successfully develop the nanorod with the aspect ratio of typically around 160 aspect ratio. This nanorod was actually, then our study was to embed this nanorod within the that chitosan PLA nanofiber that we have incorporated here. Now, that process is, you can see the XRD analysis here. So, here we have two major peaks, where the peaks at 38 degree and this is 38 degree and 44 degree. So, these two peaks, which corresponds to 111 and 200 plane of silver, silver and face centric cube silver nano tubes were manufactured. So, that is actually this is the confirmation of presence of silver and this indicates the pure well crystalline silver nanowires were obtained by solvothermal method. So, in this method, whatever we have nanowire developed, so through XRD analysis we could confirm that this nanowire was basically pure silver nanowire, and this nanowire was we used further for our experimentation, where silver nanowire we have embedded within the nanofibers. Now, for that experiment what we have done, we have used that 70-30 chitosan PLA blend, which was optimized earlier, and along with that we have added nanowire with different proportion. So, starting from 0.5%, then 1%, here it is a 3% nanowire, and then we have used 5% nanowire. At different proportion we have mixed with the this chitosan PLA blend. So, here chitosan PLA blend was optimized earlier, then we have developed our nano rod. So, this nanowire, so 70-30 chitosan PLA blend, which then it was loaded with silver nanowire at different concentration, that we have discussed 0.5%, 1%, 3% and 5%. And then what we have done, we have electrospun all these 4 different combinations, and here we have kept the same previously optimized process variables in the electrospinning. Now we can see here, as per the image which we have got, this type of nanowire were embedded. So, this is the nanofiber, the green color is showing nanofiber chitosan PLA blend, and this inside that it is a nano silver nanowire. So, here we can see that silver nanowire is perfectly aligned within the this blend chitosan PLA blended nanofiber, but not all the fibers are like this. So, there will be some fibers where silver nanowires are not perfectly embedded, but partially this nanorods are coming in the surface. So, most of the nanowires were completely parallel, like in axial direction, and enclosed inside the fibrous structure to form a coaxial structure. So, this is the coaxial structure. So, most of the cases we found this type of structures were there, but some of the fibers you can see here, in some of the fibers we found that nanowires have come out from the surface, not fully embedded. So, this is the type where, and also with this type of embedding will be there, but still that the effect of here silver will be there, and chitosan and all other chitosan's effect will be there. So, few nanowires were partially came out. So, came out from the interior wall. So, these are the different types of nanowire as we have seen. These are the completely inside the structure and partially they are been exposed. Now, EDX analysis here it shows, you can see that presence of carbon, silver, oxygen, nitrogen are there as per their proportion. Okay. And now, there are different samples we have developed. So, for sample 1 where 0.5% nanowire silver nanowires were added in the solution, and we have measured the silver percent. So, in the nano wave which we have finally produced the nano electrospun nano wave. So, there the silver percent, how much silver is present there, that we have tried to see, because not all the silvers are coming with the inside the fiber. So, here with 0.5% here we are getting 0.32% silver within that. Now, for sample 2 where 1% of silver nanowire was used, which we have found the silver content in the fiber was 0.62%, and when 3% nanowire was used. So, we could achieve 0.85%. So, that is that, and at sample 4 when we have increased the silver nanowire percent, higher percent, say 5% we have used, then we found that the silver content in the nano wave was reduced. So, that is in the blend it was reduced to 0.49%. So, finally, what we found that the sample 3 with a 3% nanowire solution, 3% content, we could get maximum silver content of 0.85%. So, then we sample 3 was, we found that it is optimized value with a higher silver content. So, this is the optimized value 3% sample 3. So, what we found that silver weight percent increases with the increase in silver nanowire loading in the mixture, and that is up to 3%, 0.51 and 3 up to 3% it increases. Then for further increase of silver nanowire in the mixture reduces the silver content. So, this may be due to the agglomeration which takes place when we increase the silver nanowire content in the mixture. So, that beyond 3% the agglomeration starts. So, that will actually that effectively reduces the silver content in the nanowire. So, the decreased residual weight was probably due to the agglomeration of silver nanowire during the electrospinning process. So, relatively if we increase the silver nanowire in the during the electrospinning, that will start agglomerating. So, what we found that 3% is the optimum value. So, we have used 3% as the our final selection. So, final selection was that chitosan PLA blend will be 70-30, and on that we add 3%, we add 3% of silver nanowire. Okay. That was our final blend, and that we have the produced the nanofiber wave by electrospinning with this combination. Then we tried to find the antibacterial activity. So, antibacterial activity here, this is simple 100% PLA, okay, 100% PLA, there is no chitosan here. So, which shows that the antibacterial activity of PLA is not there, okay. And then the trend is that with the increase in the some B, C, D and up to E, the antimicrobial activity, antibacterial activity, it is maximum almost 100% for both, and but beyond that when we go up to F, it is reducing. Now, let us see what are these samples combination. The samples combination you can see A is 100% PLA, as I have mentioned, it does not have any antibacterial activity, it is very low, and when we increase this that 30-70 was our optimum proportion for proper electrospinning. So, we are using that 70%, we can use maximum up to 70% chitosan. So, that we found that around 84 to 86 that is antimicrobial activities, and then if we increase to 0.5%, if we add when we add the silver nanowire 0.5%, and that will enhance the antibacterial activity to around 90%, from 85% to 90% it has increased. Then we further increased to 1% of silver nanowire, and we found it has further increased to 96 to 98, that means around 97%. And when we have used the PLA chitosan and nanowire, we have used 3%, which was giving higher silver content, and finally we got the this 100% antibacterial activity. So, here what we can see, this proportion 30% PLA and 70% chitosan, this blend proportion was the maximum possible chitosan we can add for proper this for proper spinnability, electrospinnability. That is why we could use maximum chitosan, which is antibacterial, and at the same time we could add maximum silver nanowire. So, these two effects results 100% antibacterial activity, and when we increase this further to 5% silver nanowire, so as we have already discussed that there will be agglomeration will be there. So, due to this agglomeration, that silver content dropped drastically, and that results in further drop in antibacterial activity. So, that is the basically reason for this trend. So, here optimum value was 70-30 PLA chitosan, and then we have added 3% silver nanowire. So, that was our optimum value, and with that, with this we have produced our final nanofibrous membrane. So, antibacterial activity of 70-30 chitosan PLA nanofibrous membrane was further found to be enhanced by incorporation of silver nanowire. So, that was our observation. 3% loaded membrane showed 100% antibacterial activity for both type of bacteria, E. coli and SRS. In case of 5%, that is antibacterial activity reduces, that is due to the agglomeration that we have discussed. So, during electrospinning process at high concentration of loading, the 5% loading, that is silver nanowire gets agglomerated, which results in drop in silver content in the final product. So, this agglomeration leads to choking of the needle, thereby amount of silver nanowire incorporation into the fiber is lower than the expected. So, initially we expected that if we go on increasing the silver nanowire, so this will add the more and more silver content, but that was not possible. But finally, what we found with the 3% we could achieve 100% microbacterial activity. That was our result. Then what we have done? We have developed the cartridge. So, cartridge first we have done, we have used the non-oven needle punch non-oven as a base. So, multi-layered non-oven structure we have developed. So, that was our substrate. On the substrate we have developed the nanowire. So, nanofiber mesh we have developed. So, this is the setup where electrospinning was done. On the substrate nanoven. So, multilayer structure was used to develop the water cartridge, water filtration cartridge. So, this type of filter cartridge we have developed here, where outer layer, middle layer and inner layer was there. So, different multi-layer we have used. Now, this is the scheme, the photograph of this cartridge. So, this cartridge was used in by replacing the normal water filter, we have used this cartridge, and then we have tested the water quality. And so, that was done in the initially, and finally, this developed cartridge was used for second stage filtration in our developed system, which we have developed. In first stage we have that we have already explained that nanoven fabric was used for that. Through the wicking we could remove the turbidity and that solid particles, and then in second stage we have removed the bacteria and all other fine particles present in the water, and we could get clean drinkable water from this. So, this study shows that here the average diameter of chitosan PLA nanofiber decreases with the increasing the chitosan content. So, that we know. So, lowest we could get to PLA and chitosan. So, 30 70. So, by increasing the chitosan content, so up to 70%. So, then what we have got, uniform silver nanowire was developed, length ranging from 7 to 12 micron, that is the range, and diameter 51 plus minus 7 nanometer was developed with the aspect ratio 159. That nanowire was developed successfully. Then in next stage we are able to embed this nanowire within the chitosan PLA nanofiber, and this nanowire. So, that what we found that 3% loading shows 100% antibacterial activity. So, for both type of bacteria. And finally, what we have done, we have successfully fabricated multilayer membrane for water filtration. So, this membrane we have developed, and this final membrane was used for the development of the water purification system, and our final stage is that design and development of prototype of 2-stage water purification system. This we have designed, and this the main idea here was that to develop the water purification system for a rural area, where we do not need any power, we need to improve the water quality to a drinkable water quality by taking the surface water from pond, from lake, canal. We can take the water and make it drinkable, and that is 2-stage. As per that, our experiment was framed. In the first stage, we removed the solid particle and turbidity large particles we have removed, and in second stage fine particles by nanowave and also by chitosan and silver we could remove the bacteria. Now, this was the final design of the prototype which we have developed here. The water from the surface, this is actually there is no power needed. We have to fill with the bucket, we can fill the water here. Okay. In this chamber water is filled. Now, here we have used the nanowire fabric which we had developed in the first stage. Needle punch nanowire fabric was used, and through wicking the water will be collected to other chamber. Okay. That was the first stage of filtration. This is the first stage of filtration. So, here we remove the turbidity and solid impurities. Okay. So, the fibers, the nanowire fabric which we have used, the optimized fabric which we have used, that was the needle punch nanowire fabric of 500 gram per square meter radial density, okay, and with the shape factor 1.3, that is we have used here the trilobal fiber. Punch density, that optimized punch density was 180 per square centimeter, and depth of penetration was 7 mm, 7 millimeter depth of penetration. So, with all this combination we have developed the fine that nanowire for first stage filtration, and where the turbidity and solid impurities are removed through the wicking action, and this is the first stage storage. So, whatever water is filtered, so that is the come out, this is the storage here. That after first stage, the water, after wicking, the water will be stored here, and then it is a second stage cartridge which we have developed. This cartridge was placed at the second stage. So, here we are trying to remove the bacteria contamination and also selective heavy metals we can control. So, here, so chitosan nanowave we have used. Okay. And then this is the storage for the second stage. You can see this is the final water, final drinkable water which we can get here it after two stage filtration, and here is the outlet which is a drinking water. These are the overall dimension. I am not going in detail of the dimension, and the photograph we can see, this is the photograph, and here we can just fill the water here, and we will get from the tap here at the bottom, we will get the filtered water. So, here the main thing is that we have to lift the water and we have filled it, and the everything is going. One is at the first stage, it is the water is transporting through wicking action, and then here filtration, the pressure which we are getting, pressure is the water head pressure, and that pressure will help in filtering water through the cartridge. Now, this is the process here. You can see we are filling the water at the top, and then the water is actually coming out from in the second stage. So, and finally, we are getting the drinking water filling there, and through the nanowire structure the water is wicked and getting collected there, and from there this through the cartridge we have developed, it is coming outside, okay, and finally the drinking water is coming. So, that was our basic system, simple system, and here what we found, the cost of per liter, it is very cheap. So, that calculation we have made, it is and this can be operated by the normal people, anyone can operate it. We do not need any expert for that. Only thing, after certain time we have to replace the cartridge, that is the only thing, and also the nonwoven fabric will be replaced or maybe washed and reused. So, that thing we have optimized, but cost of production will be very simple. Now, you can see the novel features are there. This is effective utilization of wicking characteristics. So, we are utilizing the wicking characteristics of needle punch nonwoven fabric for water purification. So, here we are utilizing the wicking characteristics of needle punch in the first, this is the first stage, and the wicking, as we know, here the frame is there, and suppose this is a frame, and here the water we are filling here, the directly surface water, and this water is being wicked here and it is collected here. So, that is the first stage filtration, and then in the second stage filtration, what we are doing? We are using eco-friendly antibacterial agent for water purification. So, in the second stage filtration, so we are using eco-friendly antibacterial agent, which is chitosan and silver nanowire. We can see that it is there is no moving part, effectively there is no moving part. So, very low level of mechanization is there, very simple in construction, no complexity, and cost wise it is a low cost is there. So, here basically for all this, no power requirement is there, cost is low, it is very simple. So, the total unit we can replace into a village, and the villager can simply fill and take the water, and only thing is that there should be a guideline how to change the fabric, and that changing the cartridge is very simple here, simple the cartridge to be replaced, and also this putting or replacing the nonwoven for the first stage of filtration is also very simple. So, this is easy to use, and unskilled people can use without involving any electric power. So, no power requirement is there. And another important is that it does not remove any minerals from the water. So, it will keep the water other properties, the health benefits intact. So, that is also advantage. So, that was our initial goal, and we could achieve that goal by different stages, as I have already explained in stage wise. And now we have completed the water purification and that the total module of protecting ourselves from the water pollution. Thank you, and we will start the next module, where we will start with the protecting the human being from mechanical threats. Different types of mechanical threats we will discuss. Till then, thank you.